All right, well, I'd like to talk to you today about a simple reliability model for human missions to Mars. And I'd like to caveat the presentation with the statement that this presentation is more about the methodology than the results, because we use inputs here out of standard sources like the Space Mission Analysis and Design Handbook and some other things like that. So they're not actual hardware values per se, but they're representative of what you would see in the real situation. This was done with a group of graduate students from Florida Institute of Technology in Huntsville, Alabama. I was their instructor and I oversaw what they did. Keep having trouble changing the slide here for whatever reason. Where should I point this thing to make it work best?
Should be right under there. The computer's right under it. Wonder it might be off.
Oh, little dongle there.
Is that actually a PowerPoint presentation?
Sir?
Is it actually a PowerPoint presentation?
No, it's not PowerPoint. Neither were the others. They're PDFs.
Huh.
But they worked, mostly. There he goes. Well, anyways, I'm just not pointing it at the right spot, I think. I see the little, I think I might see it. Okay, so this is, the analysis was done on what we call the Human Spaceflight Mission -1, and it was an undertaking to use existing and very near-term technology to land 4 astronauts on the surface of Mars, 1 year on the surface, and return safely to Earth. And so it's using all SpaceX hardware, some modifications to the Falcon Heavy second stage, about a 15% increase in performance for that, which is, we feel that was doable. And it also uses the Bigelow beam technology for the inflatable habitat. But basically, this is the diagram. There would be 4 cargo launches, and I'll describe those later, and the 1 crew launch to land on the surface and return. And there's, of course, different phases associated with each one of those. Here are the launcher and payload configurations that we analyzed. Here's a standard Falcon Heavy, and here's what we call the Falcon Heavy Extended Range, which basically adds the landing feet to the second stage, and SpaceX has already conceptualized this, and it increases performance about 15% by adding additional propellant and oxidizer to the second stage. And I'll talk more about this later, but all of the crew capsules are Dragon version 2s, outfitted properly for whatever portion of the mission. These are the launches. Launches 1, 2, 3, and 4 are payload launches. What you see here are the Bigelow expandable habitats that leave the launch pad partially inflated. They're used for storage of food and other supplies that go along. Launch 2 and 3 contains 2 Mars rover designs. We've looked at several concepts for that, including one that's based on the chassis of the Tesla Model X, I think it is. Their Tesla SUV chassis for the Mars rover. So that's interesting. And then finally, the 5th launch, after everything else is in place, functional, fueled, and ready to support human occupation, we launched the 5th launch to Mars. So from upper left, basically to the right, the basic phases would be that the Falcon Heavy Extended Range lifts off from Kennedy Space Center. The Mars Descent Vehicle, which basically lands on the surface of Mars, using the core Falcon Stage 2 for a Mars insertion burn, and then separates from the second stage and allows the Dragon version 2 to do an entry, descent, and land maneuver. By the way, the second stage is also capable of landing on Mars with the extendable landing feet. Phase 4 is the MDV, which is basically a Dragon V2 version 2, lands on the surface of Mars using propulsion. This 5 phase here shows the Earth return vehicle, which is the Payload mission number 4, which basically puts a stage 2 with power capability and another Dragon V2 in orbit around Mars and waits for the crew to finish their mission, fly the ascent vehicle back and rendezvous with the existing ERV. So again, everything uses the common Falcon hardware and the Dragon vehicle. And here's the Dragon crew vehicle. I'm sure you've seen this. This is version 2. It shows it as being used for the descent vehicle, the Mars ascent vehicle, and the Earth return vehicle that I showed you just a minute ago. I think I'm just going to use the thing here. Okay, for the study that we did, we picked Jezero Crater as the landing site. There was a study done last summer in 2015, I guess last year's summer anyway. And out of many sites that were studied, Jezero Crater came out number 1. And so we've just picked that. It's based on scientific capabilities for research, also lower risk in landing there based on the geography of the site and other considerations. And NASA participated in that study. For the crew, we will go with the MIT Advanced Biosuit. In an earlier presentation today, I also talked about a new portable life support system based on a technology derived from scuba rebreathers that are currently in use. We would employ that. The biosuit, of course, is being developed by MIT. The portable life support system is based on the Dive Right, which is Lamar Tech Incorporated Optima 2 self-contained closed-circuit electronic controlled rebreather technology. Here are the mission phases. As I said, the first 4 missions are payload and are called cargo missions, cargo spaceflight mission 1 through 4. The 4th one of those launches contains the Earth return vehicle that I showed you. Then the 5th launch is the actual human spaceflight mission. It's a crewed Earth to Mars. They explore on the Martian surface for about 13 months, I think it is. And then the Mars ascent vehicle blasts off into Earth orbit, Mars orbit, rendezvous with the Earth return vehicle. Sounds like we ought to go to that presentation. And heads back to Earth. So as part of the Monte Carlo analysis that we did, the students developed a work breakdown structure for the mission, overall mission, and assigned qualitative risks to these different tasks. These are some of the risk determinant factors that we use. These pretty much came right out of the mission design and analysis document that's out there, part of the space technology series that everybody can get. So these are typical risk determinant factors that were used. This basically quantifies for the qualitative analysis what their values are. This is just a very simple demonstration of that, in an effort to establish a risk number. Interesting stuff going on there. Anyway, if a risk is minor, it ends up with a rank of 1. It would be no measurable effect on the project, all the way up to a very high, which would be a failure mode that would cause failure of the project in the eyes of the customer. And it would have a rank of 9 to 10. Here's some of the example RDFs that are provided in the SMAD, Space Mission Design and Analysis document. Failure during launch, 0.01. Failure during assembly. Now this could be either on the ground or in-orbit assembly. We did not assume any on-orbit assembly for this mission analysis. Failure during the trans-Mars injection, very low. Only 1 in, what is that, 0.0001, 100,000, I guess. And failure during descent would be 1 in 1,000. And again, these are typical numbers. And the risk determinant factor is basically the probability of failure. It's 1 minus the reliability, as I'm sure all of you guys know. So the basic approach for the Monte Carlo analysis was to establish an analog of the mission based on the work breakdown structure that was established earlier that I showed, and come up with equivalent logic gate analogy that could be used in the Monte Carlo calculations. And this just gives an example where that carry over from the previous slide. These numbers are plugged into the equation, and we come up with an overall probability of failure of 0.0009 or 0.111 rounded up. So that's the basic premise of the calculations. Here are the qualitative analysis then based on those assumptions and applied to the various elements of the work breakdown structure. And of course the green areas represent a very low risk, the yellow are moderate risks, and the red are high or critical risks. And you see some of the things that are typical. Project risk, technical risk issues were considered to be high. Cost risk issues were considered to be high, and again, these are qualitative. And survivability considered to be high. Here's actually the two columns relate to the occurrence probability, and if it's low, that means there's a very low probability of occurrence, or RDF. If the project impact column shows if that occurs, what is the impact to the project? And again, low, moderate, and high. And those factors combined allow you to generate a risk priority number, RPN, that you can use to assign resources within the organization to mitigating the risks. Okay, well, this is the simple model. Using that type approach, the students looked at each of the phases or launches of the mission that we theorized back there. The cargo missions 1 through 3, the mission 4 that puts the ERV in orbit around Mars, and then the human space flight part of it, and ran this is what you see here is basically a point estimate where they plugged in those numbers to a similar equation that I showed you earlier and made one calculation. So this is the numbers that were associated with that. And I know this is very hard to read. For instance, these are R gates that during the ascent phase, for instance, a failure could result from mid-course corrections, launch, ascent, trans-Mars insertion burn, Mars orbit insertion burn. These are some of the things that can happen during launch and transit to Mars. Any of those could result in a mission failure. So those scenarios were built up for all of the missions. And as you well know probably, in a Monte Carlo analysis then, you take that average or predicted value based on a point estimate and apply to it a reasonable probability distribution. And you can do it based on real data. What the students did here, they just chose I believe all of these include a triangular distribution that allows like a plus or minus 10% variation in the risk determinant factor. So then for the Monte Carlo runs, and I think each one of these runs included 5,000 iterations, the program, and by the way, the software used here, which is used a lot in government circles, is the Palisades Corporation at-risk simulation software. And it does a really good job of running Monte Carlos. By the way, the latest edition of that, I think, comes standard as a Excel type macro that will also run project management files. So you can take a Microsoft project file and run it under the Excel spreadsheet as a project file and do Monte Carlo analysis on your project schedule, cost, durations, individual task durations and cost, and it's really fantastic for giving some management decision-making powers there. So anyway, that's the basic model, and the students ran that for each of the types of missions. Here's the point estimates that those numbers came from, and the calculations are identical to that simple model that I showed you earlier, and these are the point estimates for each type of missions. The 1 through 3 cargo missions included launch from Earth, entry, descent, and landing on Mars, and period. And that was the end of the mission, basically. The mission 4, cargo mission 4, is basically putting the ERV in orbit around Mars. So there's no entry, descent, and landing. Therefore, you may have noticed the mission success probability was calculated to be higher for that point estimate. And then finally, the crewed mission. And remember that while these are calculated separately, mission, for instance, cargo mission 2 would only proceed assuming acceptable results from the previous cargo mission, or depending on what might have gone wrong, cargo mission 2 might have been used to replace capability that was originally scheduled to be provided by the first cargo mission. So basically these are based on the assumption of these levels of success and no joint probability occurrence between the 5 different missions. In other words, you don't proceed to the next mission until the previous mission was successful. So here's some of the typical results, and what the at-risk software does and Monte Carlo analysis does. It generates some number of iterations where the calculation that I showed you originally as the point estimate is repeated with different values that are drawn for each probability of failure from the appropriate probability distribution. So for instance, if the students used a triangular probability distribution with the point estimate as the mean and then allowed plus or minus 10% variation, random variation, based on random number generators and such, then you would establish some 5,000 possible points within those constraints. And this is what it looks like. This is basically a probability distribution for the first 3 cargo missions, no crews. All of these have entry, descent, and landing. This is the probability distribution generated based on 5,000 iterations for the mission 4 that only puts the Earth return vehicle in Mars orbit. No EDL for that one. And I know these numbers are pretty darn hard to see. I'm not sure I can see them myself, but I think they're summarized on another page here. But these are generated then also for the crewed mission, the one in which the crew are aboard. And as it turns out, and it might be counterintuitive, but the crewed mission actually ends up with a higher probability of success than the uncrewed automated missions. And that's because the capability of the crew to respond and take contingency actions in the eyes of the students who did this study gave them a lower risk, gave that mission a lower risk. So here you see that the probability of success is basically shifted considerably to the right compared to that of the previous uncrewed missions. So also what the students ran an analysis of the cost, the mission cost. And same sort of scenario where Microsoft Project was used to generate a cost. Do you have a question, sir?
No.
No? Okay. And that baseline cost was used as the average cost for the mission. And then again, a probability distribution was assigned to each task based on a triangular distribution, and I think, again, plus or minus 10% allowance in variation. And so then those 5,000 iterations were run, and so that generates a cost probability which can be used to predict with some degree of certainty that, hey, the mission is going to, based on the baseline cost and the assumptions, it will fall within these parameters, say 90% of the time, or whatever area under the curve you might select. And again, I point out that the purpose of this paper was not to establish a concrete reliability for a manned mission to Mars necessarily. It was to illustrate the methodology. So what you would do in real life, this type of thing, you would grind down the numbers for the risk determinant factor for each phase of the mission based on hardware performance. These numbers are typically available from the suppliers of the hardware, if it's propulsion and launch equipment, and based on previous missions and that sort of thing. And then you would plug those numbers into a model similar to this and give you a feeling or not of whether you were going to have a feasibility of conducting a mission successful. This one you can see. Here's the risk analysis based on the probability distribution that was generated. A mean success of about 0.934 and 95% confidence that you would have 0.95 reliability or less. That was for the crewed mission. Here's the distribution of costs. And later, at 5 o'clock actually, I'll be summarizing another study that was done with a group of graduate students that took the overall mission and considered everything within the hardware, the orbit determinations, basically a mission planning study. But what it indicates is that with some reasonable assumptions and maybe commercial level of oversight, that you might be expected to complete a mission of this sort for $6 billion, which is a pretty fantastically low number compared to some. But as it turns out, it's in the ballpark of what the Mars One mission people are claiming. About $6 billion to make a one-way trip to Mars. So if you want to make a one-way trip, maybe you could just save up $6 billion and you're on your way. So the point of all of this is that preliminary risk analysis can be undertaken using some simplified qualitative and quantitative methodologies. It's not horse racing, although Las Vegas type techniques I think sometimes may be utilized in this sort of thing, but there's lots better ways of doing it. And over the years, of course, there's been enough tragedies within the NASA manned space program to indicate that serious attention to risk analysis and a risk management program certainly needs to be conducted routinely. And the problem is that I think it seems to be the people in the loop keep forgetting the lessons learned, and we kind of backslide into some degree of lack of attention to detail or something. Another point is that risk point estimates can be generated using previous mission success criteria or industry standard data. And although it's not necessarily most up-to-date information, as I mentioned, the handbook on space mission analysis and design does provide some guidance. There's a brand new book out, and I could provide it on a risk reference list here later, maybe. Gives some more numbers, more up-to-date than the SMAD. Further expansion of the risk assessments can be achieved using Monte Carlo analysis. And these are kind of like, given the assumptions, here's the fan out. These are probably the worst case that you could expect under these assumptions. And I think you need to know that. Do you have at best an 80% chance of success, or is it possible to achieve something that might be acceptable up in the 95 to 98% probability of success for a mission of, you define it, mission details evolve. As they evolve during a program, you can refine the analysis. Once you have a model built, unless a hardware configuration or a mission plan changes, it's a matter of upgrading your numbers, right? So you can put in more accurate numbers and refine it. And risk management is an ongoing process. You don't do an analysis, or you develop a risk management plan and set it up on the shelf and wait for something to fail, right? In order to prevent failures, you have to continuously review the mission achievements, the project achievements, what's going on, what are the problems, can we update our risk assessments, and so forth. So it's a real-time effort to make these things more accurate. And then, as I said, the commercial risk analysis packages, such as the students used here, the Palisades at risk, you can employ these things without a large code development cost. You don't have to pay software engineers to go away and, from scratch, develop a risk analysis program. The software exists. The government uses it as standard. I do a lot of work with the United States Army at Redstone Arsenal. Every time they get in a system proposal from a major contractor, they require a risk management plan be part of that, and that gets evaluated using standardized software like this, and the government results get compared to the contractor predictions, and it's kind of a sanity check. So I think it's a method of standard practice to get into the habit of conducting such risk management programs using analyses rather than seat of the pants. And Monte Carlo technique is a really good way to do it. And I believe that's the last slide. By the way, as part of this activity, a hypothetical limited liability corporation was established called the Mars Transit Bureau, which concentrated the resources of a fictional corporation or business on achieving the Earth-Mars return goal prior to 2030. And it's basically a feasibility study, and it appears doable. So there you go. Thank you. Any questions? Yes, sir.
For the cost estimate that you presented, that it was 5.5 billion and 6 billion. Was it paid by analogy or bottoms up?
Yeah, bottoms up, a limited bottoms up. What the students did, basically, they tried to price out all the SpaceX hardware that was perceived to be used. They built in some level of development, engineering development. There were program support, quality support, all the type of things that you would expend during a limited, development program. And I should have mentioned this. The entire philosophy of the HSFM-1 was the mission is to go to Mars and return safely, period. It's not to develop, a starship in the process of doing that. So I think, although a lot of people, a lot of engineers, a lot of scientists may poo-poo the concept, we have most of the technology to do that, period. You don't need a starship to go do that. You don't need Battlestar Galactica. So that's what this assumes. It is basically Bob Zubrin's Mars Direct concept. But yes, they took that work breakdown structure that I showed, they assigned reasonable hypothetical costs, put it in the model, and turned the crank 5,000 times, and that's the probability distribution that came out. And again, this is not an answer for a mission.
Work breakdown structure anywhere published. The thing is, I'm taking a class in cost estimates, and I'm having trouble with
if you'll give me your information, I'll be glad to provide it.
Sure.
There's a little report on the whole thing. It's top level. There's not a lot of detail, but it's available. Any other questions? Well, thank you very much.